good afternoon, everyone. My name is Baptiste, and I'm very happy to be here today to present you what served as my end of studies internship work, which was about BLE GATT fuzzing. So, as I said, my name is Baptiste. I'm French, obviously, but I'm not from France, the country. I'm from a French island, which is called Réunion Island, and I'm a junior R&D engineer at Quarks Lab, and my topics of interest are about embedded and wireless security. And for those of you who don't know where Réunion Island is located, here it is. So, first, let's talk about the goals of this work. So, at the beginning of the internship, two main goals were defined. The first one was about the evaluation of a framework, and the second one was about to explore an unexplored security landscape. To give a bit of context, a new framework has been developed. This framework is called WAD for wireless hacking devices, and the objectives here were to first evaluate the internal framework, and the second objective was to create a tool based on it to assess its robustness. So we decided to go for a fuzzer. And for the goal number 2, lots of security research has been done on BLE, but only a few of them targeted the HAT and the GATT layers. And for the objective here was to conduct an in-depth security assessment of these layers with our tool. So also, at the beginning of this work, we defined a methodology to be adopted. We started by the analysis phase of the specification. From this, we identify the corner cases and unspecified behaviors. From these corner cases and unspecified behaviors, we elaborated our attack scenarios. From these scenarios, we elaborated our fuzzer. And then we had to decide which targets to focus on. Spoiler, we decided to go for open source BLE stack. Then we had to develop our GATT servers. We ran our fuzzer on these GATT servers. We obtained bugs and crashes. Then we had to do the analysis of the results. Then we had to do also a lot of code reviews and the vulnerability identification. And then the last phase was to report all our findings. Okay, what is BLE? So, BLE stands for Bluetooth Low Energy. And here is a nice picture of the protocol stack. We can see that BLE is built upon several layers, but we are only going to focus on these two, the HAT layer, HAT for attribute, and the GATT layer, GATT for generic attribute. Also, what we can notice here is that there are two distinct entities that are the host and the controller, and that the host and the controller are communicating together with the host controller interface. Okay, let's detail the HAT layer. So, the HAT layer defines a client-server architecture. So, if we have a smartphone and a smartwatch, and that the smartphone connects to the smartwatch, here we will be the client, will be the server. The smartphone will be the client, and the smartwatch will be the server. Also, the HAT layer defines how the data is represented, and the different methods by which that data can be read or written. But what is an attribute? An attribute is a data structure. And here is the data structure. So, it starts with an handle on 2 bytes. Then it has a new ID field on 2 or 16 bytes. Then it has a value field of variable length, and also it has a set of permissions, which is for the size implementation specific. So the handle serves to identify the attribute we are dealing with. The UID serves to identify the type of attribute we are dealing with. Also, the HAT layer defines 30 PDUs, HAT PDUs, PDUs for protocol data unit, to exchange data. There are 6 types of HAT PDUs, commands, requests, responses, notification, indication, and confirmations. And here is the format of a PDU. So a PDU starts with an OP code. Then it has a set of parameters. And then it has an optional field, which is the authentication signature one. Okay. I'm going to introduce the notion of long attribute values, because most of our results come from this. So, how do we do when, let's say, we want to write a value where its size is greater than the actual MTU minus 1, MTU for the maximum transmission unit. So, for that, we have two PDUs that are the prepared write request and the execute write request. Here I gave the format of the prepared write request. So, it's a PDU, so it starts with an OP code. Then it has, for its sets of parameters, an handle on which attribute we want to write. Then the offset where we want to write, and also the value we want to write. Here I give a concrete example of how to use the prepared write request and the execute write request. So we have a client and we have a server. The client sends to the server this prepared write request with this set of parameters. So the first one is the handle that corresponds to a specific attribute, then the offset, 0, and then the value today is mine. The server responds with the same set of parameters, but now with the prepared write response to tell the client it's okay, you can continue. The client continues with the prepared write request on the same handle, but now the offset is different, and for the value, hardwear.io presentation day. Same. And then the client sends to the server this PDU, the execute write request with this flag, to tell the server, it's okay, now you can execute the write. And then the server responds with this execute write response to say, it's okay, everything went well. Okay, now let's define the GATT layers. So, the GATT layer defines a framework built upon the at layer, and it defines procedures and formats. So, for the formats, we have services. A service is a collection of data and associated behaviors to accomplish a function. Also, we have characteristics. A characteristic is an attribute used in a service along with properties and configuration information. And then we have descriptor. The descriptor is an optional field of the characteristic, and it contains related information about the characteristic value. So, what we have to keep in mind here is that all of these formats are in fact attributes, the data structure I was talking about before. Here is the profile hierarchy. So, we have a profile, and within this profile we have services, within services we have characteristics, and within characteristics we have values and or descriptors. There are 11 features and procedures there, that are defined by the GATT layer. Here I give a list of the 11 features, and here I give a concrete example of one procedure that is called the discover all characteristics of a service. So again, we have a client, we have a server. The client sends to the server this read by type request PDU with this set of parameters. So the two first parameters are a range of handles. So here the client is telling the server to give him all the characteristics that is in this range. Okay. So the server responds with this read by type response with this set of parameters. So trust me, this parameters corresponds to a characteristic. The client continue, but now we can see that the range of handle is shorter, okay? And we know that there are no more characteristics in this range because the server responds with an attribute not found. Okay, now that we have a good understanding of how the at and the GATT layer work, we can elaborate our attack scenario. So here, I'm only going to describe 3 out of 9 scenarios based because of time constraints. So, for the first scenario, we went from this observation. Once a client sends a request to a server, that client shall send no other request to the same server until a response PDU has been received. So, what we did here was to send in a row 2 at request PDU and to observe the behavior of the server. Okay, you might find this trivial, right? But Here I give a reference to this CV that is taken from the Swan-Tooth set of vulnerabilities. And in fact, it was exactly this for the BLE stack that was provided by ST Microelectronics to be used with their own devices. For the scenario number 2, we went from this observation. A server may limit the number of prepared write that it can queue. A higher layer specification should define this limit. Okay. What we did was to send many prepared write requests and to observe, again, the behavior of the server. And for the scenario number 3, here, we were the server, and we introduced inconsistencies in our responses. So our responses didn't comply at all with the specification. Okay, now let's shift our focus on the setup and the implementation. So we use the WAD framework. The WAD framework serves as the foundation for our Fuzzer, our tool. So WAD is an open source framework for exploring, hacking, and more generally playing with common wireless protocol. It was released at DEF CON this year, and maybe you had the opportunity yesterday to attend to the workshop that was given by Damien Coquille and Romain Kerr, the developers of the tool. And why WAD is nice to use? Because it supports wireless protocols such as BLE, ZigBee, or LoRaWAN. Also, it supports different hardware such as HCI devices, NR52, ESP32. And it provides cool features such as sniffing, replaying, hijacking, and so on. And this was our use of WAD. So we use WAD to craft and to send legitimate or custom PDUs. Also, it was very easy to handle the received PDUs. It was very easy also to populate and spawn GATT server and to modify its behavior. And also, we were able to log the packet exchanges in pickup files. So now I'm going to give an overview of our Fuzzer. So we have two parts. One part, the attack part in red and the monitoring part in blue. So we have our Fuzzer that is written in Python that implements our scenarios. This Fuzzer uses the WAD framework that is written in Python for the host to be able to send BLE packet to the targeted stack. And for the monitoring part, we monitored the targeted stack through the serial port based on protobuf messages. And also, we use pickup files, log files, and also a web application interface that was based on the Notify service. So, I'm not a fuzzing expert, but this is because, well, this is why I'm only going to give you simple a step of our strategy. So there was no mutation. We use a random strategy to fill our PDUs. For one fuzzing session only tests one scenario. Also, we decided to keep the connection during the whole session because BLE is a stateful protocol, and without that, this may lead to the discovering of more bugs and vulnerability. And also, it provides basic feedback such as the disconnection, the crash, and also told us if the stack was unresponsive or not. This slide shows the tools and the services that were used to build our test bench. So we use Raspberry Pi to be able to run our Fuzzer, and also it was connected to the targeted stack. We use protocol buffers messages that allows us to create standardized structures to facilitate the connection, the disconnection, be able to send the reset command or to log the crash logs. Also, we use the Notify service. That is an effective monitoring system that delivers real-time notification through a web application. And we use BLE Sniffer to cross-check our results. Okay, here is the help option of our tool. you have to tell to a tool if you want to fuzz a server, or if you want to be a server and to fuzz a client that will connect to you. Okay. We are releasing the tool, maybe at the end of the day. Okay. This slide shows the BLE stacks and the compatible hardware that we use. So, as I said, we use open source BLE stack. So, we use the BLE stack that it is provided with the Zephyr real-time OS. Also, we use the Nimble stack that is provided with the Minute real-time OS. And we use the Blue Droid stack that is provided with Android. And for the compatible hardware, we use NRF52, ESP32, NRF52 again, and Android smartphone and ESP32. Okay. Here, what we have to keep in mind is that the GATT servers that were used for our tests were based on the provided example by each SDK. So there were simple GATT servers. And here is a nice picture of our test bench. I'm only going to give a subset of our results. We found nonconformities, bugs, and vulnerabilities. So, for the first nonconformity, it was related to the Blue Droid stack and related to the read blob request PDU. So, if you understood how work the the prepared write request, the read blob request is the same, but for the reading part. So, here, what we can see on this Wireshark capture is that there are many read blob requests that don't have any responses, except these two. Okay, that's weird. And when we checked at the offset, all of the offsets are high. Sorry. And in the specification, it is said that if a server receives an offset that is greater than the actual value size of the value it wants to read, the server shall respond with an error. But here, even with high offsets, we have responses, okay? And when we check out to which attributes these handle corresponds to, we found out that it corresponds to first database hash characteristic and also to the client supported features characteristic. So here, these two characteristics, the database hash and the client supported features, are standardized attributes that were introduced in BLE version 5.1. But the Blue Droid stack was developed on Bluetooth version 4 when BLE was introduced. So, what I want to say here is that trying to maintain your stack up to date may introduce to non-conformities if it is not done carefully. For the first bug, it was again related to the Blue Droid stack and again related to the prepared write request. So here, what we can see first is that we have a memset that is done on this SR data structure. Okay, so here all its fields are set to 0. Then we have an offset that is obtained from a given pointer. Okay, and in the function that does the checks on the write permission, that there is a wrong parameter that is given because this SR data write request offset will always be 0. And this led the stack to answer with GATT success under very specific condition instead of a GATT not long. Yeah. Bug number 2. Again, it was related to the Blue Droid stack and related again to the prepared write request. So, first, what we can notice on this Wireshark capture is that we have the indication from Wireshark of a malform packet. I hope you can see from malform packet, okay? And also that at some point the server doesn't respond anymore. Okay, that's weird. And we find out that this behavior, that we obtain this behavior with, by sending a prepared write request to, again, specific attributes. So we send this prepared write request, we receive the prepared write response with this indication of malformed packet, and then we send this execute write request, and we observe this behavior on only on the client characteristic configuration descriptor and on the client supported features. So again, these attributes are standardized in the specification, and they were introduced in BLE version 5.1 again. So we are in the same case as for the previous non-conformity. So the interesting part. So the first vulnerability that we found was I really like this meme. Nothing will go wrong if you just follow instructions. Okay. So again, it was related to the Blue Druid stack, but here I cheated because in fact it was not related to the stack itself, but it was related to the code example that was provided by the vendor, here Expressive, to spawn GATT server on their devices. So let's say ESP32. So in the code example to spawn a GATT server, we have these two checks that are done on the offset and on the offset plus the length of the value we want to write. Okay, that's nice. But these checks are performed only if the prepared buff is not null. That means that the first prepared write request will not have his parameters checks. And for sure, just after this section, there is this beautiful mem copy where we control both the offset and the value. So we have an out of bounds write. We reported this to Expressive, and this was their response. So the impact of this issue on customer is minor, lacking any substantial consequences. But because there is a but, 7 of their code examples were impacted, and for sure they didn't communicate about it publicly. So we are curious to know how many ongoing projects are still that were based on these code examples are still impacted by this vulnerability. For the vulnerability number 2, now it is related to the Nimble stack and related to its timeout feature. So in Nimble, when a server receives prepared write requests, it starts a timer of a certain value, here 30 seconds. And if the server doesn't receive another prepared write request or execute write request, that is the normal behavior, the server shall kill the connection. Okay? But in fact, this is not a Nimble specific feature, because in the specification it said that a transaction not completed within 30 seconds shall timeout. So we just complied to the specification here. So what we find out was that in the left part, we have the malicious control, and on the right part we have the controller and the host from the let's say the server. So we find out that if we send a prepared write request to the server, it starts to unqueue the data, and then it starts a timer of 30 seconds. The host receive the servers receive response with this prepared write response. Okay, we wait about the time of the timer, let's say 29 seconds. We send to the server to terminate the connection. The controller of the server responds with connection terminated, but at the same time there is the trigger of the timeout. So the host sends to the controller to disconnect, but the controller answered with unknown connection, and then the stack is stuck in an infinite loop. Hence the denial of service. At that time, I was very happy when we found this because we received a CVE for that, and it was my first one, so very happy about this. Okay, so what we saw so far was the test that we did was on controlled environment, but what about real-world devices? So I prefer to rename this section How to Annoy Your Colleagues. Okay. So when I was hired at Quarks Lab, I had the opportunity to continue on this work, so I said, yeah, for sure. But I felt like Pablo here, I felt like something was missing. And in fact, it was testing the fuzzer on real-world devices. So this question arose, which devices to target? So this is my personal headset, and these are my colleagues' ones. So what you have to know here is that nowadays these Bluetooth audio devices, when they are used to listen to music, they use the Bluetooth Classic, but they also expose a GATT server for other features. So for sure, here I run the fuzzer only on my device, I promise. And but at the same time, I wanted to try to reproduce the denial of service that we found on the Nimble stack on my own device. So here is the GATT server of the headset. So there are plenty of services and plenty of characteristics. And here the goal was to find an enabled prepared write characteristics. So we found it here on the FE2C service that corresponds to the fast per service. And on this, in this characteristics. So this characteristic is write enabled and also it's prepared write enabled. So what we found out was that if we send a prepared write request to the headset, it responds with a prepared write response. Okay, nice. But if we send an execute write request, the headset starts the disconnection process. And at the same time, we send this find by type value request with very specific parameters. The headset sends the disconnect and receive the disconnection complete. Okay, but after a certain time, music will stop and the headset will just crash. So for the affected devices, my headset was affected, but also my colleagues weren't. Here I provide the POCs that were used, and unfortunately, this time no CVE for us. And if you are the happy owner of one of these devices, you should know that Sony released a new version this month. So if you don't want to be impacted by this, maybe think about updating your device. So now let's talk about the limitation of this work. So the first limitation was the BLE version that were used to create our attack scenarios, because we use BLE version 4.2 and not the last one, which is BLE 6, but at the time of the internship it was BLE version 5.4. And why? Is because the framework that we use, the WAD framework, currently only supports the BLE version 4.2. Also, another limitation was about the GATT servers that were used, because a poorly implemented GATT server is less likely to trigger bugs. And finally, a limitation about the analysis of the results, because I didn't have enough time to incorporate an automated analysis method. To conclude, lack of standardization of BLE stacks implementation leads to developer error. The proximity between the GATT and the implication layers may lead to more vulnerabilities. And over-the-air fuzzing is still relevant, even if not fast. And if you are interested with more details, you can check out the blog post and the related papers. Thank you. Any questions?
Thank you, Baptiste. Do we have questions in the audience? Please raise your hand if you have a question. Don't raise your hand if you do not have a question. Yes.
So I have a question regarding your test bench. I've seen that there are multiple devices. How do you run them simultaneously? And if yes, how do you manage the noise between each device sending a request? Or do you only send one PDUs at once for one scenario?
Yeah, that's it. So no noise about VPD sent.
Okay, thanks.
Any more questions in the audience? Yes.
Thank you very much for the talk. How do you find the stack for the real-world devices? Did you have to open them and see what chip was inside, or can you do it over the air?
It was a full black box work for the headset. So didn't have a stack, the firmware for the stack.
Any more questions? What was the performance of the fuzzer that you have developed?
It was slow. But yeah, it was slow. This is what I can say.
Do you have any ideas on how this can be improved?
I know that the developers of the WAD framework, maybe they will, because WAD is based on the SCAPI, and maybe it takes time. So maybe they will change it to maybe Rust code.
Everything becomes better if it's written in Rust, right? So, do you have any last question from the audience? Guess not. So let's give a last round of applause to our speaker.